Now today we'll start the last major topic, namely continuous time processes. We will basically be going through different versions of applications of such processes throughout the remainder of the time which we will have. But to be able to get from the discrete time processes to the continuous ones, we will require a bit of a setup. So we'll start slowly with reviewing things from what you know from the basic course and from what we have covered earlier in the course, and we will try building the continuous time as an extension, of the discrete one. Now, let's start quite simply with the Bernoulli and binomial distribution. Now, you know that the Bernoulli distribution is a distribution of random variables, which for every random variable can be either 1 or 0. It can be 1 with a probability p and 0 with a probability 1 minus p. Let's denote them with mi. Now those variables 1 and 0 can denote successes and failures. You do some experiment and it can end up either in a success or in a failure. Success is 1, 0 is a failure. This is Bernoulli distribution with the parameter p, where p is the probability of success. Now, if we move one step forward and count not just one attempt, but some fixed amount of attempts, we might be interested in how many of those attempts ended in a success. Now, you recall that this has already been covered. That's the so-called binomial distribution. Okay, so for a fixed n, if we want to count, if this is a model of successes or failures, for a fixed n, if we add up those ones and zeros out of n attempts, we get a variable getting us what is the number of successes among n attempts. We just denote it yn, which is sum I goes from 1 to n. Mi is the number of successes out of n independent attempts. If you think about it, if you do, for example, 10 attempts of something, you roll a dice 10 times, and you count how many times did you land a 6, you can count a probability that you got exactly 1 times 6, exactly 5 times 6, and so on. It can be shown that probability that we would have exactly k successes out of n attempts can be computed as taking the probability of successes to the power of k, multiplying the probability of failures to the power of n minus k, and multiplying by the binomial coefficient, choose k out of n. Okay, so we need to have k times success, then we need to have n minus k times failure, and we need to take into account all positions of successes. Okay, if you roll 3 dice on a table, and you want to ask what's the probability that you will have exactly 1/6 showing up, you need to take care about all options where the 1/6 can happen on the first dice, on the second one, or on the third. So you need to take into account the position of successes. Okay, so those are probabilities concerning the binomial distribution. Denoted as binom n and p, where n is the number of attempts and p is the probability of success on each of them. It can be shown that the expectation is just n times p. Yeah, here is a simple exercise. Suppose we have 10 friends. We know that on average a friend sends us a message every 6 days, so the probability that he will send us a message today is 1/6. Goes for all of the friends which we have out of those 10 people. And we want to find what's the probability that we will receive at least 3 messages today, and find out the expected number of messages which we receive today. Now, for the expected number, that's pretty simple. If I have 10 friends and for each of them there is 1/6 probability that he will send me a message, then it is 10 times 1/6, so 1.66. And if I want to compute the probability that I will receive at least 3 messages, I need to take these probabilities with n being 10, p being 1/6, and adding up those probabilities for 3, 4, 5, 6, up to 10, which can be pretty simply done by a computer and results into 22.4%. Now, does it make sense so far? Counting the number of successes where the attempts are independent and all have the same probability of succeeding. Now, what happens if we are observing a more complex problem where the number of the number of attempts is pretty large, but the the probability of success is pretty low. Okay, so what happens? What if n is large and p is really small? For example, if we are operating a server and it is available from all the internet, so the number of people who can connect to our server possibly is very large. There is millions and billions of people who have access to the internet, but the probability that any of them will actually choose our server to solve this problem is pretty small. Now, what if the expectation n times p is somehow manageable? What if this is some reasonable number, let's say lambda? Let's take a look what happens with those probabilities. This means that n we shove to infinity. We will fix p being lambda over n, and if n goes to infinity, then p goes to 0, right? Then the probabilities, the limit of n goes to infinity, choose k out of n times p to the power of k, 1 minus p to the power of n minus k. Let's see how this works out. We know what's the binomial coefficient. That's n factorial over k factorial n minus k factorial, right? And let's insert for p lambda over n. So lambda over n to the power of k, 1 minus lambda over n to the power of k. To the power of n minus k. Okay, so in the first part we have a k factorial which does not depend on n, so we can shove it outside of the limit. Here we have lambda to the power of k divided by n to the power of k, and lambda to the power of k does not depend on n, so we can also push it out. So we'll get lambda to the power of k over k factorial times the limit of n goes to infinity. And now what's remaining here? N factorial over n minus k factorial. Then 1 over n to the power of k, and now 1 minus lambda over n to the power of n times 1 minus lambda over n to the power of minus k. Now, k is a fixed constant. So if I push n to infinity, I would have here lambda over infinity, which gets us 0. So this goes to 0. 1 minus 0 goes to 1, and 1 to the power of something goes still to 1. Okay, so this part goes to 1. Now, the tricky thing is in the first part, we have actually n factorial over n minus k factorial. You recall that these can be cancelled out with here basically remaining n times n minus 1 times, and now n minus k plus 1 times something. And here we have n to the power of k, so n times n times n. And here we have n times, k times the same thing, n times something else. And here again, k times n. And we know that n over n gets us a 1. N minus 1 over n gets us a 1 in the limit. N minus k plus 1 over n still gets us a 1. So this is 1, this goes to 1, this goes to 1. So all this part goes to 1. And what we have remaining is 1 minus lambda over n to the power of n. Now, do you recall from the basic calculus, where does this go?
1.
Sorry?
1.
Not really.
Which one lambda n to the
This one, 1 minus lambda over n to the power of n.
lambda over n is going to go to 0, right? So it's
But with this n, it doesn't go directly to, well, yeah, we would have then 1 minus 0, but with this n, it gets more convoluted. Now you might recall that 1 plus 1 over n to the power of n goes to the value of e, the Euler constant, the exponential, and 1 plus x over n to the power of n goes to e to the power of x. So here we have minus lambda, so this thing goes to e to the power of minus lambda. So the limit is lambda to the power of k over k factorial e to the power of minus lambda. And this is called the Poisson approximation. If you have a really lot of attempts, but a really small probability of success in each of them, you can approximate the probabilities that you will have exactly k successes by using this approach. This is the Poisson distribution Poisson with the parameter lambda. Now, this distribution is often used. Yeah, here is the calculation by itself. This approximation is often used for counting the number of occurrences of some event in a fixed amount of time. Okay, if I am observing my server in the next minute, I have quite a lot of people who potentially can access it, but for each of those, I have a pretty small probability that they will actually access it. So I can model the probability that in the next minute, I will have exactly this and this many of customers incoming. Does it make sense?
Mhm.
Okay, if I would have n being, for example, if I would run a shop, for example, in a city with 10,000 people in there, then computing the probabilities here that, for example, exactly 3 people will come to my shop during the next hour, with this n being 10,000 or some similarly large or even larger number, I would get to computational problems pretty soon, because, well, 10,000 factorial is something really large. Okay, so this approximation is pretty useful. Now, it can be shown that used for modeling number of occurrences in a fixed amount of time. Now, if we use this representation, then it can be shown that if we increase the time period, then the only thing which happens is that the parameter lambda increases. This is pretty well, quite simple to prove, because the n just gets multiplicably larger. Okay, so if, let's say, n1 represents the number of occurrences in one period of time, so in a unit period of time with, well, Poisson distribution lambda, then nt represents the number of occurrences in a time t, okay, with the Poisson distribution with parameter lambda times t. Now, here is again a motivational element. The expectation of n1 is lambda and expectation of nt is lambda times t. Yeah, here again we see an example. Suppose we have 10,000 people in a town and 100 shops, and we know that each of the people goes shopping once every week and picks a shop at random out of those 100 shops. Okay, so we have 10,000 people. Yeah, and we want to find out about one day. How many people will come out at one day to our shop? Probability that the person goes shopping on a given day, if it picks up a day in a week at random, is 1/7, and the probability that the person comes to our shop is 1/100. Yeah, if there is 100 shops and he picks the shop at random, then the probability is 1/100. And the probability that a person goes shopping today and picks our shop is simply just the multiplication if we assume that the selection of where the people are going to does not depend on the day in the week when they are going shopping. Okay, so 1/7 times 1/100. This is the probability that any person will actually choose to go shopping that day, and that they will choose to go to us. Now, if we want to talk about probabilities that today exactly 0 people, exactly 1 person, exactly 3 people will come to our shop, we would be able to do this using the binomial distribution, but we would run into computational problems. Instead, we can use the Poisson approximation, the lambda being the expectation n times p, so 10,000 times 1/7, 100 gets us 100/7, which is a number with which we can work pretty simply. Okay, and the probability that exactly k people will come to our shop today can then be approximated with lambda to the power of k over k factorial e to the power of minus lambda. And if somebody asks us what's the probability that, for example, more than three or more people will come to our shop today, we can find it many ways, either as an infinite sum or as using the complement 1 minus the probability that 0, 1 or 2 people will come to our shop today. We will just insert in here for k being 0, 1 and 2 for the concrete lambda, and we will get the result. And now the expected number of customers in our shop is actually this lambda, and when we are asking for a longer period of time, we just multiply it by the number of days about which we are asking. Yeah, so in a week, for example, there will be on average 100 customers coming to our shop. Okay? So this way we can do a limit approach of observing the time. Yeah, if we have a really lot of attempts but a really small probability of success, then we can do this. We can do this approximation. And this goes, we will get to that. This goes pretty much the same for measuring the time between the individual successes. And you can recall that at the beginning of the course we have been establishing several important random variables. One of them was the geometric random variable, measuring the number of tries, number of attempts, until we get a first success. Now, for example, when you roll a dice, until you get a 6 and you count how many rolls you get, you will get exactly this geometric distribution. And it can be shown first that if we are observing the binomial distribution and we are measuring what are the distances between individual successes, we will see that they are exactly geometrically distributed first. And then we will see that if we make a limit approach, for example, if we would do the attempts really fast, but the probability of the attempt being actually successful would be really small, then in the limit approach, the distances, the time distances between the individual occurrences will be exponentially distributed, and the number of occurrences, the number of successes in some amount of time would have the Poisson distribution. Now this approach, counting how many successes did I have until some time, is, well, the basics of the theory of counting processes, which we will concern ourselves with. Yeah. Now, if you recall what we have been doing in the last 2 weeks, we have been dealing with processes forming discrete time homogeneous Markov chains. Now, if we go back to the binomial distribution and adding up the individual successes, counting how many successes did I have in n attempts, I can imagine this as a discrete time Markov chain, actually. Yeah, if let yn have the binomial distribution np, denoting the number of successes in n attempts. And what do we do is that we imagine this, represent this as a Markov chain. Then yn and out of n forms a homogeneous Markov, discrete time Markov chain. Yeah. Now we can say that we start at 0 with y0 being 0. Now you can imagine this process as follows. Here we have the discrete time n, and here we have the individual times of observation. And at each of those time points, we flip a coin and get either a success or a failure. And yn measures how many successes we have been already having until time n. Okay, so here, let's say we start at 0. Here at time point 1, we get tails, so we are stuck with 0. Here at time point 2, we got heads, so the process is here. Here we get heads, so the process jumps to here, and so on, and so on. Here we have tails, here we have heads, now tails, the process stays, then heads, the process jumps one up, okay? So it is basically a counting process. How many successes did we have until time n? Okay? And this is basically the sum of the individual MIs being 1 for heads and 0 for tails. Okay? Here we have M1 is 0, M2 is 1, M3 is 1, M4 is 0, M5 is 0, M6 is 1, and they all together add up to Yn, the number of successes up to time n. Make sense? Now, how would the matrix of transition probabilities for such process look like? The number of successes up to time t, up to time n. Okay. Now suppose you can imagine that we either were unlucky all of the time, or we had just 1 success, 2 successes, 3, 4, and so on. Now suppose we are at a situation where until time n we had 0 successes. We move to time n plus 1, we do 1 attempt, and where can we jump from here?
Say that again, sorry.
Suppose we have made n attempts, and they all ended up in a failure. So we are in a situation having 0 successes so far. Now we make another attempt. We move to time n plus 1. What can be the value?
Still 0.
Still 0 if we fail, or 1 if we are successful. Okay? And we are successful with the probability p. And we get a failure with a probability of 1 minus p. And this holds regardless of whether we are here or we are way there with zero successes so far. Okay? Now, what if we have just 1 success still?
Then you stay in 1 with 1 minus p probability.
And move to 2 with a probability of p. Okay? The next attempt can either be success or a failure. The success adds you 1, and the failure lets you stay on the same level as here. Like this, 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 this. Okay? And this is an example of a discrete time counting process. You go through some series of events, And each of the event can either increase your process or let it stay on the same level. It can never decrease, and it just counts how many successes did you have so far. This is actually not a matrix because it is infinite. That's a representation of an operator, but let's call it a matrix, even if it is infinite in both dimensions, right? Because if you continue to observing the process for a really long time, you will get to maybe 1000 observations. You still would have the same probabilities of either staying 1 minus p or jumping 1 up, but nothing else. Does it make sense? Now, this is one representation of such a counting process, with zeros and ones being the increments in each of the time point. This process can be viewed from a different angle using geometrically distributed random variables and thinking of them about the durations between the individual increases. Yeah. We know that, let's take a look. X1 is the number of steps until the first success. Then X2 is the number of steps until the second. Then we have X3, number of steps until the third, and so on. Okay? Or just the time which lapses between individual increments. And as you recall, at each of the, if the individual attempts are independent, if the probability of a success is still the same in each of the steps, then you know that the probability that in some amount that you will reach the first success in a series is geometrically distributed. Yeah. Then all xk's have the geometric distribution with a probability of p. This is a different representation of the same thing, of the counting process of successes and failures. Okay? Yeah, the duration between successes. And we can again imagine this process as just adding up those durations. And we know that if we count the indexes when the kth success actually occurred, then the process can be just taken as the maximum of such points where the kth success was before point n. Okay, so this is a different representation of the same process by just counting the number, well, the amount of time between the individual successes. Does it make sense? Yeah, here we have again a representation. First we had to wait for 2 turns, until we get a success. Then we needed to wait for 1, 2, 3, 4 turns to get a success. Then 1, then 1, then 3, and so on and so on. And if we add them up, continuous up one after another, just cumulatively, then we have the times until the individual successes from the beginning of the observation. And if for certain distinct n, we just find out how many successes did we have, we still are having the same process. It's called the binomial process of either staying on the same level or moving one step up. Okay? It can be seen that this process, well, starts at 0, and the increment of this process, actually, how many steps did we do? How many steps up did we do in a certain amount of time, passing from point M to N, has the binomial distribution with the number of attempts being the difference between N minus M, actually the time which skipped from M to N, the number of successes in that time is governed by the binomial distribution, and the increments of the process are independent. Yeah? The number of steps up in this time period is completely independent of the number of steps up in that time period, because at each point we either just go up or stay regardless of what happened before. That's one of the representations. Second of the representations is just finding the differences between the individual steps up, and in the individual steps up we have Bernoulli variables which can either be 0 or 1 stepping up, and that way we see that it is correctly defined from both sides, either using the geometric time between increments or the binomial increments one after another. Now you can imagine this process being used as just counting the number of successes which you had in n attempts, just doing more and more attempts. And you can imagine that this would be a simple representation for some counting process. For example, how many cars did go past the school in a period of time, when we just discretize the time and count whether there was a car in this second, in that second, in that second, in the further second, and so on and so on. Now, this of course works only if the time can be discretized simply into either seconds or days or what we have, and if the increase in each of those times, in each of those points, can only be by 1. Now you can imagine that if you would operate a server with possibly thousands requests coming within a second, then you could not simply discretize the time, and it would make sense to work with some limit approach, as we did here. This is what we will want to get to today, a process which works similarly as this, staying either on the same level or going one step at any given time point, but in a continuous time. Such processes are called counting processes. regardless of the time scale in which we observe them, we call a process a counting process if it is always non-negative, if it can have only integer values, so 0, 1, 2, 3, and so on, and if it is non-decreasing. So if we observe 2 time points, then the point which is further in time can see the process only either staying on the same level or increasing, never decreasing. Okay? So this is a counting process often used to model the number of occurrences of something in a given period of time. Yeah, if I start looking on the street and counting the cars which have passed, I will just be increasing the number of my raised fingers for every car running, and in this case, the time durations between the individual cars will of course be continuous. So we want some representation of such a process with continuous time. Yeah, we want the increments and t minus ns, so the number of events which happen in the interval from s to t, to be simply represented, and we want to generalize over the simple binomial process by having possibly continuous or different times between the individual events. Now, for this, we use the Poisson process. The Poisson process is exactly that, a continuous generalization of the binomial process. Now, the Poisson process has 2 equivalent definitions, which we will prove that they are actually equivalent. And we can use both of them to find out its properties. Poisson process is such a process which counts how many observations, how many occurrences of some event that we have up to time t, if the times which lapses between the occurrences are exponentially distributed. So let x1, x2, and so on be independent and identically distributed, exponentially distributed random variables, and let t n be the sum of k goes from 1 to n, and t0 being 0. Then the Poisson process nt with nt being the number of x's, well, the number of t's below the small t, maximum of m's, so that Tn is less than or equal to T, is called the Poisson process with intensity lambda. Yeah, this is how the Poisson process actually might look like. Here we have the individual axis, exponentially distributed durations between arrivals. And here we have the t's, counting the time up to the fifth, up to the nth arrival. And we are just by the Poisson process, we are just counting how many of these jumps did we have up to time t. Okay?
I'm sorry, that word is intensity lambda?
Yes, intensity. Yeah, the xi's are times between jumps. The ti's are times of the jumps. And mt gives us the number of jumps up to time t. Okay? Generally speaking. Now, it can be shown that the process can be defined from the other way, not using the times between increments, but the distribution of the process at some given time. Yeah, we can define the process alternatively by saying that it starts at 0, its increments between points t and s have the Poisson distribution with parameter lambda times t minus s, and that the increments of the process are independent. This is a completely different way of looking at the process, similar as we did before, as we looked at the binomial process from the perspective of binomial increments or geometrically distributed times between events. It can be shown, we will get to that later, that those definitions are actually equivalent, and both of the representations can allow us to simply answer questions regarding the behavior of the process. Okay, if we, for example, know that the process, well, the number of increments follows the Poisson process, yeah, for example, the number of people coming to our server, we know that the number of people who arrive to our server between time point 10 and time point 20 has the Poisson distribution with parameter lambda times 20 minus 10. Okay, so equivalently, and t being non-negative is a Poisson process with intensity lambda whenever it starts at 0 and 0 is 0, mt minus ns as the Poisson distribution with parameter lambda times t minus s, and the increments are independent. Yeah, so for the binomial process which we have been dealing with before, we know that the times between occurrences are geometrically distributed. Yeah, we basically are flipping a dice until we get heads, so until we get an increment. And for the Poisson process, the times between the individual occurrences are exponentially distributed. That's a continuous distribution, which we will study further. The binomial process can jump only in integer times. The Poisson process can jump in actually any time point on the non-negative real scale. And for the binomial process, the distribution at point n was binomial. For the Poisson process, the distribution at point t is Poisson with parameter lambda times t, and the expectation is for the binomial process, the expected number of jumps until time t, until time n is the amount of time times the probability of jumping. For the Poisson process, the expected number of jumps until time t is the intensity times the length of how it has been running. Okay? Now, for the binomial process, the thing is that the expectation at point n can never be larger than n. Yeah, if you have a coin and you keep flipping it and count how many heads do you have until the nth toss, the number of heads can never be larger than n, because you get either heads, so you add one, or tails, you do not add one. Okay, so you never get something larger than n. For the Poisson process, if we take a look at this thing, if the distribution of the times between jumps has a really small expectation, you can see the process jumping really, really fast. Okay, so then it depends on the actual lambda, on the intensity of the process. Now, if you recall what we have been talking about regarding the geometric distribution, you know that it is actually memoryless, meaning that the probability that we will need to wait for getting heads in a series of tosses does not depend. If we compute a conditional probability that, for example, we need to wait for more than 7 tosses, if we know that we have already waited for 3 tosses, we can restart the process right as if we were at the beginning, just by saying it's the probability that we will need to wait for more than 7 minus 4. This is the memoryless property. We have seen this on the first tutorial. Now, the same goes for the exponential distribution. The exponential distribution is just a continuous generalization of the geometric distribution. Yeah, you keep flipping the coin really fast, but the probability of getting heads is pretty small in each of the flips, and altogether n, the number of how fast you flip, and the number of the probability of success altogether work to some reasonable ratio lambda. Now the thing that the distributions of the increments, exponential here, or binomial, or geometric there, that they are both memoryless, gets us to the fact that the processes both can be represented as homogeneous Markov chains, meaning that they are forgetting the history, and the probability of jumping up does not depend on how long the process has already been running. If we take a look at this graph, we could at any point restart the process, slice it here, and then just move up, and it would look the same. We can just, the probabilities of jumping up in any given amount of time are the same regardless of how long the process has already been running. So the memoryless property helps us, and we can then represent those counting processes as Markov chains. For the binomial process, it's a discrete time Markov chain. Then for the Poisson process, it is a continuous time Markov chain, which we will define later. It is just continuous generalization. Now, the times, I have said that the times between the increments need to be distributed geometrically. Needs to be distributed exponentially. The exponential distribution as itself is often used for measuring time until something happens. Here we use it to measure time until we get an increase in the process, until we get a count and move up. And we will see how it looks like, we'll see how it behaves, and how it can be used then to, well, prove the equivalence of those definitions, and how it simplifies things. The exponential distribution has the density looking like this: lambda times e to the power of minus lambda t for non-negative t's, and 0 otherwise. The exponential distribution, we see that, well, let's say variable t has the exponential distribution with parameter lambda if the density is lambda times e to the power of minus lambda t, for t negative, else it is 0. Now, this distribution is pretty simple to work with. We can prove how it behaves, what's its expectation, pretty simply. We can find out how the probabilities concerning this distribution are computed pretty simply also. Okay, let's take a look. This is how the density looks like. E to the power of minus something is just the flipped tail of the exponential, so the decreasing tail of the exponential, and depending on the parameter lambda, if lambda is large, then it is heavier here. If lambda is small, it is heavier there. Now, let's take a look at an example where we will see what the properties of the distribution are. Okay, so let's say that t is the time spent waiting for a bus. And let's say that it is exponentially distributed with lambda being equal to 1/10 in minutes. And first we want to find out the expected time until the bus arrives. Now you recall the expectation of a continuous random variable is computed as, well, x times fx dx. Okay, but let's hear it, yeah, so the expectation of t, that's an integral minus infinity to infinity x times fx dx. Okay, here the density is 0 below 0. So we take just the above part, integral from 0 to infinity x times lambda e to the power of minus lambda x dx. Okay. Now what can we do with this integral? Any ideas?
Anything to the minus infinity is going to be 0?
E to the power of minus infinity is 0, yes. But first we need to find the primitive function. Now, if we would take, let's take a look. If we would take the derivative of the e to the power of x, we would get e to the power of x. Good. The integral of e to the power of x dx is also e to the power of x, right? And now, if I put a constant, yeah, that's indefinite integral, so just, let's say plus c here. If I would have e to the power of, let's say, ax, and take the derivative, what would I get? What would happen with this constant?
ax times e times e to ax.
Yes, we use the rule for taking derivatives of chain functions. Yeah, this is the outside function which gets derivative to the exponential, but we need to multiply it by the derivative of the inside function, which is ax, so the a goes here. Good. And if I take an integral of e to the power of ax dx, what happens with the a?
You just pass it multiplying, right?
It goes here. Okay, so if we wouldn't have this x here, we would be able to use the minus lambda here and divide, take the primitive function. Okay, now here we have this x. Can we rid of it some way? Sorry? Not directly. That's not a chain rule for, but it's called a bit differently.
X dot y dash plus y dot x dash.
No, that's for derivatives. That's not for integrals.
So those are like multiplication of two functions? No.
It's not. The integral of a product is not product of integrals. It's not. Other ideas? Now, if I were to take the derivative of x, what would I have?
1.
1. Yes. And how can I switch integrating into taking derivatives? Integration by parts, right?
Integration by parts.
Yeah, the integral of, let's say, uv is the primitive function of uv minus the integral of small u, capital V. Like this. You recall basic calculus?
Yes.
Good. So for us, this capital U is x. So we just write it down, so x. Then we need to take y times lambda. Then we need to take the integral from e to the power of minus lambda x. We know that e to the power of minus lambda x over minus lambda from 0 to infinity. And then I would have minus, and now the derivative of x, which is 1. And now lambda times e to the power of minus lambda x over minus lambda dx. Okay. Let's first work with the first part. If I have, now these lambdas get cancelled, I don't care about them that much, but they are just positive constants. I have here x to the power, x times e to the power of minus lambda x. For x goes to infinity, what happens? Yeah, for lambda being a positive constant. If I have such an expression, x times e to the power of minus x, where does this go? If I have a polynomial times exponential, the exponential always wins. Yeah, it is faster either growing or decreasing. So this is like infinity times 0, but this 0 is faster, so this goes to 0. And if x goes to 0, I'll have here 0 times e to the power of minus 0, which is 1. So it goes also to 0. So this whole thing goes to 0. We don't care about it. Okay? And lastly, here we have minus minus, which get cancelled. Lambda and lambda, which get cancelled. So I have just the integral from 0 to infinity e to the power of minus lambda x. So I integrated e to the power of minus lambda x over minus lambda from 0 to infinity. At infinity, e to the power of minus infinity is 0 minus, and now e to the power of minus lambda times 0 over minus lambda. E to the power of 0 is 1. Minus minus gets a plus, so it is 1 over lambda. In this case, 1 over 10, which is 10 minutes. The intensity, 1 over 10, is actually giving us the number of buses per the amount of minutes. So I have 1 bus per every 10 minutes. Making sense? Now,
So expected time is 10 minutes?
yes.
I don't know, intuitively, I would say that the expected time will have to be lower than 10, because there are more occasions where you wait less than 10 minutes, than there are occasions where you wait 10 minutes. Just like intuitively, not...
But when looking at this graph, for lambda being 1 over 10, this would be quite far to the right with quite large probabilities. Okay? Intuitively, there is a pretty large bulk of the distribution here, but it does not decrease that fast. So basically, you still have some distinct probability that you will need to wait, for example, for 20 or more minutes. Okay? And the expectation of 10 minutes gives us, well, the middle point, which weights out the probability, which weights out the density. Okay?
Yeah.
It doesn't seem intuitive on the first glance. For example, if you would, yeah, telling that there is actually one bus every 10 minutes in such a grid would lead you to thinking that if you arrive here, then you would need to wait for the bus for smaller time, right?
Yeah.
But this is not how the exponential distribution works. The exponential distribution gives us some of the distances small, some of the distances large, but the average being 10 minutes. Okay? Now, the next part asks us what's the probability that we will need to wait for more than 5 minutes. Yeah, so the probability that the waiting time will be larger than 5 minutes. Now, how can we compute this?
Complementing from 1 to 5.
We can. One minus probability that it is less than or equal to 5. Okay. And how do we compute this?
By adding the probability of waiting 1 plus 2 plus 3 plus 4.
Okay, now what is the probability that we will wait exactly 1 minute? When working with this continuous distribution.
Just the area
From where to where?
from 0 to 1.
Not really. From 1 to 1. It is infinitely small
Yeah.
with respect to the whole mass of the continuum. Okay. So in this case, we do not add the probabilities because the individual points have 0 mass. We need to talk about whole subintervals. Okay. So if we take a look at this density, how do we find the probability that d is less than or equal to 5?
So from 0 to 5, the area.
Yes, the area from 0 to 5. Okay, so I'll get 1 minus integral from 0 to 5, and now the density, so lambda times e to the power of minus lambda x dx, which is 1 minus going from 0 to 5, lambda e to the power of minus lambda x over minus lambda from 0 to 5. These lambdas get cancelled. And so I will have 1 minus plus e to the power of minus lambda times 5 minus gets us a minus e to the power of minus lambda 0, which is 1, which is e to the power of minus lambda times 5. That's one possibility of how could we compute this. The second would be just integrating directly from 5 to infinity. Okay, the integral from 5 to infinity lambda e to the power of minus lambda x dx. So I will have lambda e to the power of minus lambda x over minus lambda from 5 to infinity being minus e to the power of minus infinity, which is 0, minus e to the power of minus lambda 5, which is e to the power of minus lambda times 5. And I know that lambda is 1 over 10, so e to the power of minus 5 over 10, e to the power of minus 1/2, which is 0.606. Okay, this is called a survival function. It is denoted as capital S of t, meaning that it is the probability that we will need to wait for more than t, and it is, if we just insert t here, e to the power of minus lambda times t. This notation, this term, comes from the reliability theory, when we are counting the time not until something good happens, but until something bad happens. If we are, for example, observing a machine and measuring the time until it breaks down, then this survival function gets us the probability that the machine will survive for more than t days. Okay? And lambda is then not the intensity of arrivals, but the intensity of failure. Okay, so if we operate the machine over and over, and whenever it gets broken, we replace it by a new one, or we repair it, then the lambda gets us the expected number of intensity of failures, so the number of failures per given amount of days. Okay? Now, what would happen if we would like to compute the probability that t is larger, let's say, than 7, if we know that t is larger than 5? Yeah, the probability that altogether we need to wait for more than 7 minutes, if we know that we have already been waiting for 5 minutes and no bus came.
We take rate from 5 to 7, maybe?
Not really.
5 to 7 divided by...
This is a conditional probability, and we know that the conditional probability of A given B is the probability of them both over the probability of the other. So here we have the probability that P is larger than 7, and at the same time P is larger than 5 over the probability that P is larger than 5.
But it's the same as t is larger than 5. What? The intersection.
Careful, here we have 5 and here we have 7. Larger than 7 is this, larger than 5 is this. What's their intersection?
Yeah,
Larger than 7, right? So this gives us t being larger than 7, and the probability that t is larger than something is given by the survival function. So it is e to the power of minus lambda times 7 over e to the power of minus lambda times 5. If we put it together, we will see that it is e to the power of minus lambda times 7 minus 5. giving us e to the power of minus lambda times 2. And what is that?
To the power of
difference between 5 and 7.
Exactly. This is the probability that t will be larger than 2. Yeah? And generally, for the exponential distribution, the probability that t will be larger than, let's say, t plus s, if we already know that we waited for s or more, is the probability that t will be larger than t for all t s. Negative. This is called the memoryless property. Now, does it make sense? This distribution, as a continuous distribution, is one of the most simplest to deal with in the context of what we want to get to, Markov chains, which forget their history. And if we use the times between the individual arrivals as exponentially distributed, meaning that we can safely restart the process at any given time point and forget about the history, gives us, at the end, the Markov property. Now, if we would like to study the buses one after another, yeah, suppose we stay on the platform and let the buses come and go. And we count how many buses there were in a given amount of time. We would arrive to the Poisson process. Okay, if we would start here we would have, well, x1, the time until the first bus came, x2, the time until the second one came, x3, the time until the third, well, between the second and the third, then might be longer, x4. Then we can, let's say, nt, yeah, this has the exponential distribution with parameter lambda, this has also the exponential distribution with parameter lambda, and so on. Nt, the number of buses up to time t has the Poisson, follows the Poisson process with intensity lambda. And the probability that in a given amount of time we would have just seen exactly k buses has the Poisson distribution with parameter lambda times t. Okay, so the probability that in amount of time t we would have exactly k buses is lambda t to the power of k over k factorial e to the power of minus lambda t. Yeah, the probability that in t minutes there were k buses. And when we get to back what we have computed exactly here, the probability that in 5 minutes there were no buses, it is lambda times 5 to the power of 0 divided by 0 factorial e to the power of minus lambda times 5 What is lambda times 5? Something to the power of 0. That's 1. 0 factorial. It's 1. And we are left with this, e to the power of minus lambda times 5, which is the probability that the first bus will arrive after 5 minutes. Okay, the equivalent that during the first 5 minutes we have seen an O bus is that the first bus came after more than 5 minutes. Okay, and this way the Poisson representation of the Poisson process using the Poisson distribution is connected with the exponential distribution of the inter-arrival times. Okay, does it make sense?
Yes.
Good. So next time we will see how this is rigorously proven that this is equivalent, and then we will see how it relates with the Markov chain theory, and we will see couple of examples of applications. Okay? Good. So thank you and see you on Wednesday.
Thank you.
Thank you.
You're welcome.